there and then acting here, as long as they're separate. There are two things which have nothing to do with each other, and then the order doesn't matter. And mathematically, this is called bifunctoriality. If you read this in a category theory book, I'm sure nobody immediately thinks about it like this.
That's true.
But that's it. That's what it is. Category theory books are awful, as a matter of like appealing to intuition. And as far as I know, there exists no good text which sort of gives you categories as this very simple, intuitive thing, except for a paper I recently wrote, which appears in the book "What is Category Theory?" and it just explains it like this.
What was the name you said?
A paper I wrote in a book which is called "What is Category Theory?" Which should have come out.
Published by Polymetrica.
Yes,
just come out about 3 months ago.
Just came out about 3 months ago. And there I use it like this. So here is the symmetry axiom. Like I said, symmetrical categories. What does symmetry mean? Symmetry means the following. I've got two systems here. Like it's easier if you go like I've got black pen and I've got green pen. And putting the top of green pen and then exchanging black pen and green pen is the same thing as exchanging black pen and green pen and then taking the top of green pen. That's basically what's written down in this picture. So it's like all silly things which you want to make explicit. The amazing thing is how much power, computational power, this is going to give us. Like this ridiculously silly assumption. Now you see.
How do you know that you have made enough silly things explicit?
Because of what you can prove with it. It's really, and there have been and again there is empirical evidence from the computer scientists who write programs for distributed machines and have to be sure that they made every little silly thing sufficiently explicit that the thing works. Because your computer doesn't reason and it's not going to intuitively add anything to it. So this is like computer science as empirical evidence of my formalization of the nature of reality.
But you don't want to allow braided monoidal categories? Because I think you should have a braiding in there.
If the thing is, okay, the thing is, sometimes you could like weaken. So here I've got this crossing, and sometimes for many purposes, I'm not going to talk about it today, but like you can give yourself more expressibility by instead of taking this, you take two variants on this.
Nuts.
Yes. Like if I don't want to lose these two things, like I say, I gave it from one end to another before. If I don't want to do that, I can't go on anymore. I'm stuck.
You have to practice it.
And that's this. And this can give you a lot more expressibility to encode, for example, anionic behavior, phase sort of things, boson, fermion sort of stuff. So people have been using that specifically for that reason, to have more expressibility. For what I'm doing today, that's not needed. That's not needed, because this is actually, this is not saying something about physical reality, this is more adding additional degrees of freedom, like for example the quaternions or something like that, just to encode something extra. That's what this can help you to do.
When it comes to entanglement, it's not so clear to me that it isn't in fact telling us something about topological structure that is at the level of the real world. That's certainly what
this I can clarify. Like because where Kaufman and Monica use this is to encode different universal unitary transformations. So to distinguish between different unitary transformations and being able to say something about universality about a set of gate, they use this as a language to encode your possible unitary transformation. It's just like adding a bit of extra to your language. To say, I'm not going to talk about the structure of the unitaries. Like that's completely. I said this in the beginning. I consider that as a boring stuff in this talk. So it's the structure of the isomorphisms, to say. But you can add that, and it's important for many things. But I'm just talking at an even more basic level.
Yeah, I appreciate that. So there is a different viewpoint as to where
it's not a different viewpoint. It's very compatible. It's just
okay. Well,
it's not different. There is no conflict there.
Okay.
It's just adding expressibility. It's like adding two new words.
I think Luke Kaufman would disagree with you that it's not adding something more than just two new words. But we can come back to that.
Yeah. I have no problem with whatever he says. So I don't have any problem with what he says. I find it completely comparable. But anyway, one important thing is, we've been talking about these types, and part of the structure of a symmetric monoidal category is that you have units for tensor. So, A tensor something is equal to A. Now, what in the just as an example, what is this in the Hilbert space? I. Well, this is Hilbert space, you tensor it with something and you get something isomorphic in the Hilbert space. What? This is complex numbers. So this is not completely trivial, this thing. I call it nothing here, no system. The no systems formally in Hilbert space quantum mechanics means complex numbers, so it's a very non-trivial thing. There's a lot of structure in the no system. And how am I going to depict this stuff? How am I going to depict this stuff? I'm going to depict this stuff by triangles, from nothing to something. So, a morphism of type I to A will be a triangle. From nothing to something. A state. It's a state. So this is for me a state. Let's not write it F, let's write it phi. Now, how does this look in Hilbert space quantum mechanics? This is here. So you say, in Hilbert space states are vectors. But of course each vector can be written as a map which assigns 1, the complex number 1, to the vector. So this is a linear map which defines the state, which defines a vector. Yes? Everybody agrees with that?
Now, just a question. Can you treat that no system as a terminal object in category theory?
No.
No.
You don't want to do that.
Why?
Because it's wrong. It doesn't behave like that. It's wrong. You're going to see why.
Okay.
Why? Let's just look at... actually, I'm going to now give the answers. So everybody understands this, that you can represent a vector just as a linear map, which assigns 1 to that vector. Yeah, so this is the type here is from complex numbers to Hilbert space. Now I'm going to look at these kind of things. From the unit to the unit. Which means from complex numbers to complex numbers. How many maps are there from linear maps from complex numbers to complex numbers?
Want to send them to 0 too?
No, there are as many maps from complex numbers to complex numbers as there are complex numbers.
Yeah.
If you just assign 1 to that particular complex number, say S. Yes? So the maps from complex number to complex number, which I will depict as diamonds. Why diamonds? Because if you take a triangle and you glue a triangle to it, you get a diamond. This will be numbers. This is a number. This is a number. And in my theory, this will play the role of probability or something like that. Probabilistic weight. So you see, at this level, at the moment I was just like axiomatizing compounders, but there is space for numbers there. You see, the numbers are sneaking in already. And as we will see later, the ball rule will just sneak in, for example, in this setting. So how do you produce? So we have ket, we have